400 kilometers above the surface of Europa, the ice is broken, not shattered, folded. Long ridges cross the frozen shell in parallel lines, some of them stretching for thousands of kilometers, as if something beneath the surface had pushed, released, and pushed again. There is no wind here to smooth the ridges down. There is no rain. There has been no weather at all, in any sense we would recognize, for longer than complex life has existed on Earth. And yet the ice keeps moving, slowly, continuously, as though something underneath it is still awake. That is the strangeness at the center of tonight's story. Jupiter itself, the planet everyone knows, is not where this trail leads. Jupiter is a world of gas and pressure, a place where nothing solid has ever stood. But circling it, 4 small worlds keep their own quiet history, and one of them, Europa, smaller than our own moon, wrapped in ice tens of kilometers thick, may be hiding an ocean larger than every ocean on Earth combined. Beneath that ice, darkness, pressure, warmth from below, and chemistry that has had 4.5 billion years to do something with itself. What if there is life down there? Not intelligent life, not anything that would recognize us as we would recognize it, but life in its most basic form, a chemical process that sustains and repeats itself, the way it did on Earth, in the dark, before there was a sun to see by. Tonight we follow that question from the beginning. How Jupiter itself came to be. How its moons formed in the debris left behind. How one small world came to keep an ocean secret for billions of years. And what it would take, what it is already taking, to finally ask the ice what it knows. We will move slowly, the way this story deserves. There will be no shortage of things we do not yet understand, and the keeper will say so plainly, each time it happens, rather than pretend otherwise. This is not a story about certainty. It is a story about the patient work of finding out. Consider, for a moment, what it took for anyone on Earth to even suspect that Europa had an ocean at all, given how little direct information a distant, icy moon typically offers a curious observer. From a telescope, the moon is nothing more than a pale, marbled dot, crossed by faint tan lines that early observers assumed were cracks in solid rock. For most of the 20th century, that assumption held. Europa was treated as a dead world, a ball of ice, frozen through, with nothing beneath the surface but more ice, and beneath that, stone. It took spacecraft, magnetometers, and decades of careful argument to overturn that picture. The ocean was not observed directly. It was inferred, piece by piece, the way a detective assembles a case from evidence that never quite shows the culprit's face. This is worth sitting with, because it tells you something about the kind of question we are asking tonight. Nobody has seen Europa's ocean. No probe has touched its water. What we have is indirect. Magnetic fields that bend in ways only a conductive fluid could explain. A surface that behaves like something floating, rather than something fixed. And a chemistry, glimpsed in trace materials on the ice, that hints at what might be dissolved below. Science, at its most honest, often works this way, building confidence not from a single decisive glimpse, but from the accumulated weight of many small, imperfect observations that all point in the same direction. So when we ask whether there is life beneath Jupiter's ice, we are really asking 2 separate questions, and it is worth keeping them apart from the outset. The first is a question of chemistry. Does Europa have the raw ingredients that life, as we understand it, requires? Liquid water, the right elements, and a source of energy to drive reactions. The second is a much harder question, one that no mission has yet been built to answer directly, whether those ingredients, given enough time and the right conditions, actually assembled themselves into something that could be called alive. Tonight, we will spend most of our time with the first question, because it is the one we can currently answer with real confidence. The second question remains open. It may remain open for a very long time. The keeper will not pretend otherwise. What follows is not a story about a discovery already made. It is a story about a discovery still being pursued, slowly, expensively, imperfectly, by people who have spent entire careers trying to answer a question that may outlive them. We begin 4.5 billion years ago, with a disk of gas and dust collapsing around a newborn sun, and a fragment of that disk large enough to become the largest planet in our solar system. Everything that follows, the moons, the ice, the ocean, the question of life, begins there. Before we return to that early disk of gas and dust, it helps to understand where we are going and how we will get there. This documentary moves through 7 stages, each one a piece of the larger question. We will begin with Jupiter's own violent birth, because a planet's history shapes everything that later orbits it. From there, we will follow the formation of its 4 largest moons, discovered by one man with a homemade telescope in 1610, and ask why one of them turned out to be so different from the rest. We will examine the ice itself, what it hides, and how scientists first came to suspect an ocean was underneath it at all. We will spend time with the chemistry of that ocean, and with the strange precedent Earth itself provides, in trenches at the bottom of our own seas, where sunlight has never reached, and life thrives regardless. We will meet Europa's neighbors, Ganymede, Callisto, and a small moon of Saturn named Enceladus that may be telling us something similar from a different corner of the solar system. We will follow the machines that have been built to ask these questions directly, some already on their way. And finally, we will sit with what it would mean for Europa and for us, if the answer to tonight's question turned out to be yes. The record is far from complete, but it is not empty either. There is a great deal here worth taking slowly. It is also worth saying, before we begin, why Jupiter's system deserves this kind of attention in the first place, rather than the outer edges of the galaxy or the stranger worlds now being found around distant stars. There is a difference between speculation and evidence. When astronomers speak of exoplanets that might support life, they are working from starlight alone, the faint dimming of a star as a planet passes in front of it, a chemical signature teased out of light that has traveled for years to reach a telescope. It is extraordinary work, but it is also distant work, several steps removed from anything resembling direct evidence. Europa is different. It is close enough that spacecraft have already flown past it, close enough that a mission is already on its way there now, close enough that within this decade, real data, not modeling, not inference from starlight, but direct measurement, will begin to arrive. That nearness is part of why this particular question, of all the questions we could ask about life beyond Earth, is the one worth spending an entire evening with. 4.5 billion years ago, the sun had not yet finished forming. Around it spun a wide, flattened disk of gas and dust, the leftover material from the cloud that had collapsed to create the sun itself. Most of that material would eventually fall inward, feeding the young star, or scatter outward into the dark. But some of it, in the colder outer reaches of the disk, began to do something else. It began to stick together. The process started small. Grains of dust, no larger than specks of ash, collided and clung, forming pebbles. Pebbles collided and clung, forming boulders. Given enough time, and there was a great deal of time, spread across a region of space so vast that a single orbit could take years, those boulders grew into bodies large enough to pull in more material through their own gravity. Somewhere beyond what is now the asteroid belt, in a region cold enough for water and other volatile compounds to freeze solid rather than boil away, one of these growing bodies had an advantage. Ice, it turns out, is abundant in the outer solar system, and a young world that can capture ice as well as rock has far more raw material to work with than one confined to stone alone. This was the beginning of Jupiter. Within a few million years, a blink, by the standards of planet formation, it had grown large enough to begin pulling in the surrounding hydrogen and helium gas directly from the disk, the same light, abundant elements that made up most of the sun itself. This is the detail that separates Jupiter from a world like Earth. Earth built itself from rock and metal, slowly, over tens of millions of years, and never grew large enough to hold on to much of the lighter gas around it. Jupiter reached a critical size early, while the gas was still there to be captured, and once it started pulling gas inward, the process accelerated. More mass meant more gravity. More gravity meant faster accumulation. Within a few million years, Jupiter had become the dominant object in the outer solar system, more massive than every other planet combined, twice over. This is worth pausing on, because numbers this large tend to lose their meaning through repetition. If Jupiter were hollow, more than 1,300 Earths could fit inside it. Its great red spot, a storm that has churned continuously for at least 300 years and possibly much longer, is itself wider than Earth. To put the storm's scale in more direct terms, a traveler circling its outer edge at the speed of a commercial jetliner would need the better part of 2 full days simply to complete one loop, without once crossing the storm's center. And yet, for all this, Jupiter is not a solid place. There is no surface to stand on, no ground beneath the clouds. Descend far enough, and the atmosphere simply thickens, from gas to a strange fluid state where hydrogen behaves like a metal, to a core that remains genuinely uncertain, obscured by pressures no laboratory on Earth can fully replicate. This uncertainty is not a failure of observation. It is a limit built into the physics itself. Jupiter's interior pressure at depth exceeds anything that has ever been produced artificially, which means models of its core are built from extrapolation rather than direct measurement. Some models suggest a small, dense core of rock and ice at the center, gradually being dissolved and mixed upward into the surrounding hydrogen. Others suggest something closer to a fuzzy, poorly defined boundary rather than a distinct core at all. The truth is that nobody currently knows for certain, and any documentary that claims otherwise is telling you more than the evidence supports. What matters most for tonight's story is not what happened inside Jupiter, but what happened around it. As the young planet grew, it did something that shaped everything that followed. It created its own miniature version of the solar disk that had formed it. Gas and dust caught in Jupiter's gravity began to spin around the planet in a flattened ring, and within that ring, the same slow process of collision and accumulation began again, on a smaller scale. Dust became pebbles. Pebbles became small bodies, and in time, 4 of those bodies grew large enough to become worlds in their own right: Io, Europa, Ganymede, and Callisto, the 4 largest of what are now 95 recognized moons. These 4 were not identical twins, despite forming from the same surrounding material and around the same host planet. Their differences trace directly back to distance, how close each one sat to Jupiter as it formed, and how much heat Jupiter's own gravity delivered to each of them during that early, chaotic period. Io, closest to Jupiter, ended up almost entirely rocky, its ice long since driven off by heat and radiation. Its surface today, the most volcanically active in the solar system. Callisto, farthest of the 4, kept its ice largely intact and remained geologically quiet, its ancient, cratered surface almost unchanged since formation. Ganymede and Europa sit between these extremes, and it is here, closer to the middle of that spectrum, that the story of tonight's question truly begins. The amount of material available to build these 4 moons is worth appreciating on its own terms, because it explains why the Galilean satellites grew so much larger than most other moons in the solar system. Jupiter's early circumplanetary disk, though far smaller than the solar disk that built the Sun and planets, was still substantial enough in mass and material to construct 4 worlds, 2 of which, Ganymede and Callisto, rank among the largest moons anywhere in the solar system, with Ganymede alone larger than the planet Mercury. This scale reflects Jupiter's own enormous gravitational reach. Even a modest fraction of the material captured during the planet's formation was, In absolute terms, more than enough to build a family of moons, unlike anything else observed around another planet. Europa, the smallest of the 4 large moons, ended up with a composition that turned out to matter more than anyone initially suspected. It is mostly rock, with a metallic core, but wrapped around that rocky interior is a shell of water, some of it ice, and, as we will see, quite possibly a great deal of it liquid. At the time these moons formed, nothing about Europa looked especially different from its neighbors. It was simply one of 4 icy worlds circling a gas giant, cold and distant, the kind of place early astronomers assumed had frozen solid the moment it finished forming, and had changed very little since. It would take nearly 4 centuries after its discovery, and the direct intervention of spacecraft, to learn that this assumption was wrong. Europa's transformation, if it can even be called that, did not happen across a single dramatic period the way a mass extinction reshapes a planet in a geological instant. It happened as a permanent condition, sustained quietly since the moon's formation and continuing, as far as anyone can tell, into the present. Whatever heats Europa's interior today has likely been heating it, in some form, for billions of years. That heat is not simply left over from formation, cooling gradually the way a planet like Mercury has cooled. It is generated continuously by a mechanism we will return to shortly, and it may be the single most important fact about this small, icy world. For now, it is enough to know this. Europa was built from the same cold, ordinary material as its neighbors, in the same violent nursery around a forming gas giant. And somewhere in that unremarkable beginning, conditions came together that would leave it, uniquely among its siblings, holding something the others do not. There is one more piece of this early history worth including before we move on, because it explains a detail that will matter later: the discovery of these 4 moons in the first place, and the surprisingly ordinary circumstances under which it happened. In January of 1610, a mathematician in Padua turned a small, handmade telescope toward Jupiter and noticed 4 points of light near the planet that had not been recorded before. Over several nights, he watched them shift position, moving back and forth around Jupiter in a way that made clear they were not fixed stars but bodies in orbit. Galileo Galilei had found the first moons ever observed around a planet other than Earth, and in doing so, had found direct, visible evidence that not everything in the heavens circled the Earth itself, a fact that would place him in direct conflict with the authorities of his time, but which stands today as one of the founding observations of modern astronomy. He named them, collectively, the Medicean stars, after his patron. History settled on a different name, drawn from Greek mythology, the Galilean moons, in honor of the man who found them, watching quietly through a lens no larger than a modern telescope's smallest component. 400 years before any spacecraft would confirm what he could only see as 4 unexplained points of light, Galileo was not observing in isolation, even though history often remembers the discovery as his alone. Within days of his own observations, the German astronomer Simon Marius reported seeing the same 4 points of light, and a minor, occasionally heated dispute over priority followed, one that has never been fully resolved to every historian's satisfaction. What both observers agreed on, working independently with similarly modest instruments, was the basic fact that mattered most: 4 bodies orbiting Jupiter, moving in ways that placed them firmly outside any model of the universe, with Earth at its unmoving center. That 2 observers, working without knowledge of each other's efforts, arrived at compatible conclusions using nothing more than glass lenses and careful nightly records, is itself a small, early demonstration of something this documentary returns to repeatedly. Confidence in a scientific claim grows strongest not from a single observer's word, but from independent observation converging on the same result. Galileo could not have known what lay beneath the ice of the smallest bright point in his lens. He had no way to measure temperature at a distance, no way to detect a magnetic field, No way to imagine that the world he was watching might be hiding an ocean larger than his own. He saw only a moving light, and reported it faithfully, without embellishment, exactly as any careful observer should. It would take more than 3.5 centuries, and machines capable of traveling farther than any human being ever had, before that plain point of light began to reveal what it had been holding on to, quietly, the entire time. By the middle of the 20th century, most astronomers had settled on a fairly modest picture of Europa. It was small, colder than almost anywhere on Earth has ever been, and covered in ice. Beyond that, there seemed little reason to expect complexity. A world this size, this far from the sun, should have frozen through completely not long after it formed. The way a cup of hot water left outside on a winter night eventually freezes solid from surface to bottom. Ice, once frozen this deeply and for this long, does not typically melt again without an external source of heat. And Europa, orbiting far beyond the warmth of the sun, did not appear to have one. This assumption held until spacecraft began arriving in the Jupiter system with instruments capable of testing it directly. Pioneer 10 and Pioneer 11 passed through in the early 1970s, offering the first close images, though at resolutions too coarse to reveal much surface detail. It was Voyager 1 and Voyager 2, arriving in 1979, that changed the picture. Their cameras returned images of Europa's surface that immediately puzzled the scientists reviewing them. The moon was not covered in craters, the way an old, geologically dead world should be. Its surface was instead crossed by long, intersecting lines, reddish-brown streaks against pale ice, some running for thousands of kilometers, crossing and recrossing each other in patterns that looked less like impact damage and more like something had been actively reshaping the surface, again and again, over long stretches of time. A world that old should be scarred by billions of years of impacts, the same way the moon above Earth is scarred, or the way Callisto, Europa's own neighbor, is scarred almost beyond recognition. Europa had strikingly few craters, and the ones present were often shallow, their original depth apparently softened over time in a way that suggested something beneath the surface had allowed the ice to slowly relax and settle, smoothing out damage that would otherwise have remained sharp and permanent for billions of years, the way it has on Callisto. The simplest explanation for a young-looking surface on an old world is that something is resurfacing it, erasing old damage and replacing it with new material, faster than impacts can accumulate. On Earth, this happens through weather, erosion, and plate tectonics, forces driven ultimately by heat from within our planet's core. On Europa, there was no obvious source for anything similar, and yet the evidence for resurfacing was difficult to argue with. The explanation, when it arrived, came from an unexpected direction, not from Europa itself, but from its inner neighbor, Io. Voyager 1's cameras captured something no one had seen on another world before, an active volcanic eruption, a plume of material rising hundreds of kilometers above Io's surface. This was startling on its own. It became more than startling once scientists worked out why Io, a small rocky moon with no internal heat source of its own by any conventional measure, could be this volcanically active in the first place. The answer was tidal heating, and understanding it requires picturing something usually left out of simpler descriptions of orbits. Io does not travel around Jupiter in a perfect circle. Its orbit is very slightly stretched into an ellipse, a shape maintained by a subtle gravitational tug-of-war with Europa and Ganymede, whose own orbits are locked into a precise mathematical relationship with Io's. For every orbit Ganymede completes, Europa completes exactly 2, and Io completes exactly 4. This relationship, called an orbital resonance, means the 3 moons repeatedly line up in the same configurations, and their gravity tugs on each other in a way that never quite cancels out. The result, for Io, is a moon that gets stretched and released on every orbit, as Jupiter's overwhelming gravity pulls harder when Io is closer, and less hard when it is farther, while its sibling moons complicate the geometry further still. This constant flexing generates heat through friction, the same basic principle that warms a piece of metal bent rapidly back and forth by hand. For Io, small and close to Jupiter, the effect is extreme, driving the volcanic activity Voyager photographed in real time. For Europa, farther out and therefore subject to a gentler version of the same squeezing, the effect is smaller, but it does not need to be large to matter. It only needs to be large enough to keep a layer of ice from freezing completely through. And once scientists worked through the physics, tidal heating turned out to be entirely capable of doing exactly that. This was the moment Europa stopped being a simple, frozen world in the minds of planetary scientists and became something worth a much closer look. If tidal flexing could keep Io's interior molten enough to drive constant volcanic eruptions, a gentler version of the same process, acting on Europa's water rather than rock, could plausibly keep a layer beneath the ice liquid rather than frozen solid. The surface features Voyager had photographed, the long, crisscrossing lines, the near absence of craters, suddenly had a coherent explanation. They were not simply cracks in dead ice. They were the visible record of a surface being actively reshaped from below, consistent with a shell of ice floating on something that could move. He would take another spacecraft, arriving nearly 2 decades later, to turn this plausible explanation into something closer to direct evidence. Voyager had shown what Europa's surface looked like. It would fall to a mission named Galileo, fittingly enough, after the man who first found this small moon through a handmade lens, to look beneath that surface and to find the strongest evidence yet for what Europa's long history of ice and motion had been hiding all along. It is worth taking a moment to sit with how strange this mechanism actually is, because tidal heating runs against a common intuition about warmth in space. Most of us think of heat as something that radiates outward from a source, the sun warming a planet's own internal fires cooling gradually since formation, the way a kettle cools once removed from the stove. Tidal heating works differently. It generates warmth from motion itself, from the simple, repeated act of being stretched and released by a nearby gravitational field. No fire is required, no radioactive decay, no leftover heat from formation, no external source of light. Only the relentless, patient pull of a much larger neighbor, applied over and over again, for as long as the orbital arrangement that causes it continues to hold. And that arrangement, the resonance-locking Io, Europa, and Ganymede into their precise 4:2:1 relationship, is itself a product of deep time, stabilized not at formation but gradually, over millions of years, as the moon's orbits shifted and settled into the configuration that persists today. Left undisturbed, this kind of resonance can remain stable for a very long time indeed, which is part of why scientists consider tidal heating a reliable, ongoing process for Europa rather than something that happened once and stopped. The moon is not coasting on residual warmth from 4.5 billion years ago. It is being actively squeezed in the present by the same gravitational relationship that has likely persisted, with only minor variation, for most of the solar system's history. This detail changes how we should think about Europa's ocean, if it exists. An ocean kept liquid by leftover formation heat would be a temporary feature, cooling slowly and inevitably toward a frozen, dead end, the way a cup of coffee left on a counter eventually reaches room temperature regardless of how hot it started. An ocean kept liquid by tidal heating is a different kind of feature entirely, one sustained continuously by an ongoing mechanical process, as stable, in principle, as the orbital resonance that drives it. This is not a puddle slowly evaporating. It is closer to a furnace that has been quietly running without interruption for longer than complex life has existed anywhere in this solar system. None of this proves an ocean exists. Tidal heating explains how Europa could keep a subsurface layer liquid, given the right internal structure, but it does not by itself confirm that structure is actually present. For that, Scientists needed a more direct kind of evidence, something that could not be explained away by surface appearance or orbital mechanics alone. They needed to look inside the moon itself, without ever touching it, using nothing but the way Europa responded to the powerful magnetic field surrounding its parent planet. That evidence arrived through the Galileo mission, and it remains to this day among the strongest indications we have that Europa is hiding something the Voyager probes could only guess at from a distance. There is a further consequence of tidal heating worth including here because it connects directly back to the orbital resonance discussed earlier and explains why this mechanism is expected to remain reliable rather than fading over time. The same gravitational interactions that stretch and release Io, Europa, and Ganymede also very gradually exchange orbital energy between the three moons in a way that has kept their resonance locked in place, with only minor drift, for a very long span of the solar system's history. Some models suggest the current configuration has persisted largely unchanged for at least several 100 million years, and possibly for a much longer stretch than that, though the exact history remains an active area of research. This stability matters because it means Europa's heating has not been a brief, unusual episode limited to some earlier period of the moon's history. It has most likely been an ongoing, largely uninterrupted condition for a very substantial fraction of the 4.5 billion years since Europa first formed, precisely the kind of long, undisturbed timescale that matters most when considering whether chemistry, given enough time, might eventually organize itself into something biological. The clues had been accumulating for 2 decades by the time Galileo arrived, a scarred history of resurfacing, a mechanism capable of explaining it, an orbital relationship stable enough to sustain that mechanism indefinitely. None of it, on its own, was proof. Together, it was enough to justify sending a spacecraft equipped to look for something no camera could photograph directly. Not ice, not cracks, but the electromagnetic signature of liquid water, hidden kilometers below a surface that had been keeping its secret since before there was anyone around to ask the question at all. Jupiter possesses the strongest planetary magnetic field in the solar system, roughly 20,000 times more powerful than Earth's own. This field extends millions of kilometers beyond the planet itself, engulfing all 4 Galilean moons within a vast, invisible structure called the magnetosphere. For most purposes, this magnetic field is simply a feature of the environment the moons happen to sit inside. For scientists trying to determine what lies beneath Europa's ice without physically drilling through it, that field became something far more useful: a tool. The principle behind this tool is not exotic. It is the same one used in a school laboratory to demonstrate electromagnetic induction. Move a magnet near a conductive material, and the material will generate its own weak magnetic field in response, opposing the change. Jupiter's magnetic field, as it happens, is not perfectly aligned with the planet's spin axis, which means that as Jupiter rotates, the field sweeps past each of its moons at a slightly changing angle. If Europa were made entirely of solid rock and ice, with nothing conductive inside it, this changing field would pass through with little effect. But if Europa contained a layer of conductive fluid, and salty water is an excellent conductor, that fluid would respond to the changing field by generating a secondary field of its own, a kind of magnetic echo, detectable by any spacecraft flying close enough with the right instruments. The Galileo spacecraft, which entered orbit around Jupiter in December of 1995 and continued operating for 8 years afterward, carried exactly the instrument needed to look for this echo, a magnetometer, sensitive enough to detect subtle variations in the surrounding field during each close flyby of Europa. Between 1996 and the mission's final years, Galileo passed close to the moon repeatedly, and each time, the readings showed the same pattern: a secondary, induced magnetic field, varying in exactly the way theory predicted it should if a layer of salty, electrically conductive liquid existed beneath Europa's icy shell. This was not a single, dramatic detection settled in one pass. It was a pattern confirmed across multiple flybys, cross-checked against alternative explanations, and gradually strengthened as more data accumulated. Could the signal instead be explained by something other than liquid water, a different kind of conductive rock, perhaps, or some effect of the ice itself at certain temperatures? Researchers tested these alternatives directly, and none of them reproduced the specific pattern Galileo observed as convincingly as a global layer of salty liquid water did. By the end of the mission, the induced field evidence had become one of the most widely accepted lines of support for a subsurface European ocean, discussed in planetary science literature not as speculation, but as the leading, best-supported interpretation of real, repeated measurements. Alongside the magnetic evidence, Galileo's cameras and other instruments added further support, filling in details the earlier Voyager images had only hinted at. High-resolution imaging revealed regions of Europa's surface where the ice appeared to have broken apart entirely and refrozen into a jumbled, chaotic texture. Areas scientists came to call chaos terrain, blocks of surface ice that looked, in the most literal sense, as though they had once floated freely, shifted position, and then locked back into place as the surrounding material refroze around them. One especially well-studied example, a region known informally among researchers as Connemara Chaos, spans an area roughly the size of a large city, its surface a jigsaw of tilted, rotated ice blocks that fit back together, imperfectly, like a puzzle reassembled by someone missing several of the original pieces. Detailed measurements of how far individual blocks have shifted from their original positions allow researchers to estimate the viscosity of whatever material once allowed them to move, calculations that consistently favor a soft, mobile layer beneath the surface rather than rigid ice resting directly on stone. This is difficult to explain if the ice sits directly atop solid rock. It becomes far easier to explain if the ice floats atop something that can move, a liquid or slushy layer capable of allowing surface blocks to drift, rotate, and reassemble before the whole system refreezes at the surface once again. Taken together, the picture that emerged by the early 2000s looked something like this. Europa's outer shell is composed of water ice. Its thickness still genuinely debated, but generally estimated somewhere between 15 and 25 kilometers, though some models allow for a thinner shell in certain regions. Beneath that shell lies a layer of liquid water, kept from freezing by tidal heating, salted with minerals leached from the rocky interior below, and deep enough, by most estimates, to hold roughly twice the volume of water present in every ocean on Earth combined. Beneath the ocean, a rocky mantle. At the very center, a small metallic core, similar in basic composition to the cores of the rocky inner planets, including Earth's own. It is worth being honest about the limits of this picture, because a documentary that only reports confidence would be doing this story a disservice. The exact thickness of the ice shell remains uncertain, with different measurement techniques and models producing different estimates that have not yet been fully reconciled. Whether the ocean is in direct chemical contact with the rocky seafloor below, or separated from it by an intervening layer of high-pressure ice, is likewise unresolved, and this particular uncertainty matters more than it might first appear. Direct contact between liquid water and rock is central to one of the most promising theories for how life might have begun on Earth itself, a theory we will return to in the next chapter. If Europa's ocean is sealed away from its rocky floor by ice, the chemistry available to it changes substantially, and so does the strength of the case for habitability. Scientists do not currently know, with confidence, which scenario is correct. The record here is incomplete, and it will likely remain incomplete until a mission specifically designed to investigate Europa's interior arrives and gathers data that Galileo, built primarily to study Jupiter itself, was never equipped to collect. What Galileo did provide, definitively, was the shift from plausible hypothesis to well-supported scientific consensus. Before Galileo, the existence of a European ocean was an informed guess, built on surface appearance and orbital mechanics. After Galileo, it became the dominant, evidence-backed explanation, accepted by the overwhelming majority of planetary scientists studying the Moon, not proven beyond all possible doubt, since direct sampling has never occurred, but supported by multiple independent lines of evidence that together leave little room for a more mundane alternative. The Moon Galileo Galilei first saw as an unexplained point of light in 1610 had, through a spacecraft carrying his own name, revealed itself to be something almost nobody had expected: an ocean world hidden in plain sight, orbiting the largest planet in the solar system. Galileo, the spacecraft, did not end its mission quietly once this evidence had been gathered. In September of 2003, with its fuel supply nearly exhausted and its instruments degraded after years of exposure to Jupiter's radiation, mission planners made a deliberate decision to send the spacecraft on a final, destructive plunge directly into Jupiter's atmosphere, rather than leave it drifting, uncontrolled, in the Jupiter system indefinitely. The reasoning behind this choice speaks directly to how seriously scientists had come to take the possibility of a European ocean by that point. An uncontrolled spacecraft, its orbit gradually decaying over the following decades, risked eventually crashing into Europa itself, potentially carrying microbial contamination from Earth on its surfaces, despite pre-launch sterilization procedures. Rather than risk contaminating a moon increasingly understood as one of the most promising candidates for life in the solar system, NASA chose to destroy Galileo deliberately, burning it up in Jupiter's atmosphere, preserving Europa's ocean uncontaminated for whatever mission and whatever more sensitive test might eventually come next. A useful comparison exists in the sheer scale of Europa's ice, if the numbers are put into terms drawn from more familiar experience. If the low end of current ice thickness estimates is correct, at roughly 15 kilometers, the ice covering Europa's ocean would still be deep enough to bury Mount Everest with room to spare, and to do so not just at one point, but across the entire surface of a world with more total surface area than Africa and Australia combined. This is not a thin, fragile crust prone to easy rupture. It is a shell substantial enough to have protected whatever lies beneath it from the vacuum, radiation, and temperature extremes of open space for the entire span of Europa's existence, while still, as the evidence in this chapter suggests, remaining thin enough in places and dynamic enough overall to permit some exchange of material between the ocean and the surface above. There is one more piece of evidence worth including here, more recent than Galileo, and considerably more contested. Beginning in 2012, astronomers using the Hubble Space Telescope reported occasional detections of what appeared to be plumes of water vapor erupting from Europa's South Polar region, rising as high as 200 kilometers above the surface before falling back. If real, these plumes would represent a direct sample of subsurface material ejected into space where a passing spacecraft could, in principle, fly through it and analyze its composition without ever touching the ice itself. Enceladus, a small moon of Saturn we will meet later in this documentary, produces plumes of exactly this kind, and their detection there is far better established. For Europa, the picture has remained frustratingly inconsistent. Some observing campaigns detected signs of plume activity. Others, conducted under similar conditions, detected nothing at all. This kind of intermittent result is difficult to interpret cleanly. It could mean that Europa's plumes are real but rare, perhaps linked to specific points in its orbit when tidal stress on the ice is at its strongest, opening temporary vents that reseal shortly afterward. It could also mean that some of the earlier detections were affected by instrumental noise or atmospheric interference, and were never plumes at all. Planetary scientists remain divided on this question, and it is presented here honestly, as an open matter rather than a settled one. What is not in dispute is that if the plumes exist, And if a future mission manages to fly through one at the right moment, it would offer one of the most direct tests imaginable of what Europa's ocean actually contains, without drilling, without landing, without disturbing the ice at all. For now, the ice keeps most of its secrets to itself. What can be said, with reasonable confidence built from decades of layered evidence, is this. Somewhere beneath that battered, cracked, endlessly resurfaced shell, water exists in liquid form, warmed by forces set in motion at the moon's formation and sustained ever since by the same gravitational relationship that first revealed itself through Eo's volcanoes. Whether anything living has ever made use of that water remains, for now, a separate question entirely, one that depends not just on the presence of liquid water, but on chemistry, energy, and time, three ingredients we have not yet fully accounted for. It is to that chemistry, and to a set of discoveries made not on Europa, but in the deepest, darkest trenches of Earth's own oceans, that we turn next. For most of the 20th century, scientists thinking about life beyond Earth worked from a single, powerful assumption. Sunlight was essential. Every ecosystem on the surface of our planet, from a forest canopy to a coral reef, ultimately depends on photosynthesis, the process by which plants and certain microbes convert sunlight into chemical energy. Remove the sun, the assumption went, and you remove the base of the food chain, and with it, any realistic possibility of a thriving ecosystem. This assumption shaped how scientists thought about habitability across the solar system for decades. And it is part of why Europa, orbiting so far from the sun that sunlight reaching its surface is roughly 1/25th as intense as sunlight reaching Earth, was not taken especially seriously as a candidate for life until relatively recently. That assumption was overturned not by a discovery on another world, but by a discovery in Earth's own oceans, in a place nearly as alien to human experience as the surface of another planet. In 1977, scientists aboard the submersible Alvin, exploring the seafloor near the Galapagos Islands at a depth of roughly 2,500 meters, found something nobody expected to see at that depth. Dense clusters of living organisms clustered around openings in the seafloor where mineral-rich water, heated by volcanic activity below, poured out into the surrounding ocean. These openings, now known as hydrothermal vents, existed in complete darkness, far below any depth sunlight can reach. And yet life there was not merely surviving, it was thriving, in astonishing abundance. Tube worms taller than a person, dense beds of clams and mussels, entire communities supported by something other than sunlight entirely. The something turned out to be chemistry itself. The water pouring from these vents carries dissolved chemicals from deep within Earth's crust, particularly hydrogen sulfide, along with dissolved metals and minerals. Certain bacteria living near the vents had evolved a way to extract usable energy directly from these chemical reactions, a process called chemosynthesis, functioning as an ecological foundation in exactly the roles sunlight and photosynthesis play everywhere else on Earth's surface. These bacteria, in turn, support everything else in the vent ecosystem, forming a complete food chain that has never needed sunlight at any point in its history, and, as far as researchers can tell, never will. This discovery did more than add an unusual ecosystem to the biology textbooks. It fundamentally changed how scientists thought about the requirements for life, anywhere. If sunlight was not, in fact, essential, if chemical energy alone, drawn from mineral-rich water interacting with volcanic rock, could sustain a complete and thriving ecosystem in total darkness, then the search for life elsewhere in the solar system no longer needed to focus exclusively on worlds that received meaningful sunlight. It could reasonably extend to any world with liquid water, the right chemistry, and a source of energy from within, regardless of how far that world sat from the sun. Europa, dark and distant, suddenly looked less like an unlikely candidate and more like a genuinely plausible one. The parallel between Earth's hydrothermal vents and Europa's hypothesized ocean floor is, admittedly, not perfect, and it is worth being precise about where the comparison holds and where it does not. Earth's vents are powered by volcanic heat, driven by plate tectonics, a process unique, as far as we currently know, to our own planet. Europa has no confirmed plate tectonics. What it does have, as established in the previous chapter, is tidal heating, a different mechanism, but one capable of producing a similar underlying result: warmth generated continuously within a rocky interior, potentially driving hydrothermal activity at the boundary between Europa's rocky mantle and its ocean above, in much the same way Earth's volcanic heat drives activity along its own seafloor vents. Whether this hydrothermal activity actually occurs on Europa remains, again, an open question rather than a settled fact. It depends heavily on the unresolved issue raised in the previous chapter, whether Europa's ocean sits in direct contact with rock or whether a layer of high-pressure ice separates the two. If direct contact exists, the conditions for something resembling Earth's vent chemistry become genuinely plausible. Mineral-rich water, heated from below, interacting with rock in ways that could generate the same kinds of chemical energy gradients that sustain life in Earth's steep oceans. If the ocean is instead isolated from the rocky floor by intervening ice, that particular chemical pathway becomes far less available, though it does not necessarily rule out other, less well-understood sources of chemical energy within the ocean itself. There is a third ingredient worth naming clearly, alongside liquid water and chemical energy, because habitability depends on more than simply having the right raw materials present. It depends on time, specifically, the amount of time those materials have had to interact, undisturbed, in a stable environment. This is where Europa's ocean, whatever its precise internal geometry, may hold a genuine advantage over almost anywhere else being considered in the search for life beyond Earth. If tidal heating has kept this ocean liquid continuously since Europa's formation, as the stability of the orbital resonance driving that heating suggests it likely has, then Europa's ocean has existed, in some form, for something close to 4.5 billion years. For context, current estimates place the origin of life on Earth itself somewhere between 3 and 4 billion years ago, meaning Europa's ocean may have existed for as long as Earth's own oceans have, quietly running the same fundamental chemistry, entirely undisturbed by surface weather, meteor impacts affecting biology directly, or any of the environmental upheavals that have repeatedly reshaped conditions on Earth's own surface across deep time. None of this constitutes evidence that life exists on Europa. It constitutes something more modest, and worth stating precisely. It establishes that the basic requirements scientists currently believe life needs, liquid water, a plausible source of chemical energy, and enormous stretches of undisturbed time, may all be present simultaneously in Europa's ocean, in a combination matched by very few other locations currently known in the solar system. Chemistry is not biology. A world can hold every ingredient necessary and still, for reasons not yet understood, hold no life at all. But a world holding all three ingredients is a far more compelling subject for investigation than one holding only some or none. And it is this convergence, water, energy, and time, arriving together in one small, ice-covered moon, that has moved Europa from a scientific curiosity to one of the 2 or 3 most seriously considered targets in the entire search for life beyond Earth. There is a further layer of chemistry worth mentioning, drawn not from Earth's oceans but from Europa's own surface, because it may play a role in supplying the ocean below with something it would otherwise lack. Europa's icy shell sits directly within Jupiter's punishing radiation belts, bombarded constantly by charged particles trapped in the planet's enormous magnetic field. On most worlds, this kind of radiation would be regarded purely as a hazard. On Europa's surface, it appears to be doing something more constructive as well, breaking apart water ice molecules and any trace compounds mixed within them, and reassembling the fragments into new molecules, including oxidants, chemical compounds capable of driving energy-releasing reactions when they eventually come into contact with reduced compounds rising from below. If these surface-generated oxidants are gradually transported downward, carried into the ocean through the same cracking and resurfacing processes described in earlier chapters, as chaotic terrain forms, breaks, and refreezes, they could supply Europa's ocean with an additional source of chemical energy, independent of whatever hydrothermal activity may or may not be occurring at the seafloor. This would mean Europa's ocean is not chemically closed off from the rest of the Moon, waiting passively on internal processes alone, but rather connected, however slowly, to a surface actively being reworked by Jupiter's radiation. Estimating exactly how much material moves from surface to ocean and how quickly remains difficult, and figures proposed in scientific literature vary considerably depending on the assumptions used. But the basic mechanism, radiation transforming surface ice into useful chemical compounds, eventually cycled downward into the ocean below, represents one more piece of evidence that Europa's interior may not be as chemically isolated or as chemically impoverished as its cold, distant appearance would suggest. One additional wrinkle deserves mention before moving past Europa's chemistry entirely, because it illustrates how interconnected these various lines of evidence actually are. Spectroscopic analysis of Europa's surface, conducted using both ground-based telescopes and instruments aboard the Galileo spacecraft, has detected the presence of hydrated sulfate salts and other compounds across much of the Moon's icy shell, concentrated most heavily in the same chaotic, actively resurfaced regions discussed in Chapter 2. The presence of sulfate salts is itself informative, since salts of this kind are difficult to explain through pure ice chemistry alone, and instead point toward material that originated in a liquid, mineral-rich reservoir before reaching the surface, consistent with an ocean beneath the ice periodically exchanging material with the surface above it, exactly as the chaos terrain would predict. Some researchers have also proposed that at least part of the yellowish-brown coloration visible across portions of Europa's surface may result from sulfur compounds, potentially delivered in part by Io's own volcanic activity and captured within Jupiter's surrounding magnetosphere before settling onto Europa's ice. If correct, this would mean Europa's surface chemistry is shaped not only by processes internal to the Moon itself, but by material actively exchanged between Jupiter's 4 large moons, linking the volcanic violence of Io, discussed in Chapter 2, to the quiet, ice-covered chemistry of Europa in ways that are still being worked out in detail. Chemistry alone cannot answer the question this documentary is built around. It can only narrow the range of worlds where that question is worth asking with real seriousness, rather than idle curiosity. By that standard, Europa has earned its place among a very short list. What remains is not a matter of theory, but of measurement, instruments capable of testing these ideas directly, rather than inferring them from a distance. Some of those instruments are already built, already launched, already crossing the solar system on their way toward this small, ice-covered moon. Before we meet them, though, it is worth turning briefly to Europa's neighbors, because the story of ocean worlds in our solar system did not stop with one small moon of Jupiter. It extends outward, to Saturn, and to a discovery that answered, more directly than anything found at Europa so far, one question this chapter has left open. Ganymede, the largest moon in the solar system, larger, in fact, than the planet Mercury, orbits just beyond Europa, one step further from Jupiter, in the same chain of resonant orbits that keeps Io, Europa, and itself locked into their precise gravitational relationship. Like Europa, Ganymede shows evidence of a subsurface ocean, detected through similar means. Magnetic field measurements, first gathered by Galileo and later refined by observations from the Hubble Space Telescope, which tracked subtle shifts in Ganymede's faint auroral activity consistent with a layer of salty water beneath the surface, influencing the Moon's interaction with Jupiter's magnetic field. Ganymede's ocean, if current models are correct, may be considerably larger than Europa's in absolute terms, simply because Ganymede itself is a larger world with a thicker overall ice shell. But this greater thickness cuts against Ganymede's habitability prospects rather than supporting them. Current estimates place Ganymede's ice shell at somewhere between 80 and 150 kilometers thick, several times deeper than Europa's, with the ocean beneath likely sandwiched between layers of ice rather than resting in direct contact with rock at all. Under the pressures found at that depth, water can form exotic phases of ice that remain solid even at temperatures well above normal freezing, meaning Ganymede's ocean, despite its impressive volume, may be almost completely sealed off from the kind of rock-water chemical interaction discussed in the previous chapter as a potentially critical ingredient for life. A large ocean, in this case, is not automatically a more promising one. Depth and isolation can matter more than size. Callisto, the outermost of the 4 Galilean moons, presents a similar puzzle from a different angle. Its ancient, heavily cratered surface, visibly different from Europa's youthful, resurfaced ice, suggests a world that has changed remarkably little since its formation, consistent with weaker tidal heating at its greater distance from Jupiter. And yet Callisto, too, shows some magnetic evidence hinting at a possible subsurface layer of liquid water, buried even deeper than Ganymede's, beneath an ice shell that may extend more than 100 kilometers down. If a Callisto ocean exists, it likely sits in an even more isolated, even more chemically stagnant state than Ganymede's, with correspondingly weaker prospects for anything resembling active biological chemistry. It is worth pausing to compare Io's fate with Europa's more directly, since the 2 moons sit close enough together that the difference between them illustrates how sensitive tidal heating actually is to distance. Io, roughly 40% closer to Jupiter than Europa, experiences tidal flexing intense enough to keep its interior almost entirely molten, driving volcanic eruptions so continuous and so powerful that the moon's surface is thought to be resurfaced by fresh lava on a timescale of only about 1 million years, among the fastest resurfacing rates known anywhere in the solar system, rocky or icy. This is, in effect, too much of a good thing. Io's heating is so extreme that any water the moon once held has long since been driven off entirely, leaving a world of sulfur, silicate rock, and near-constant volcanic violence, wholly unsuitable as a candidate for life by any definition currently in use. Europa, sitting just one step farther out, receives a gentler version of the same physical squeezing, enough to keep a subsurface ocean liquid, not enough to boil it away or drive the kind of extreme volcanism seen at Io. The margin separating a moon stripped of water entirely from a moon with an ocean twice the volume of Earth's own turns out to be startlingly narrow, a difference of only a few 100,000 kilometers in orbital distance. Among Jupiter's 4 large moons, then, Europa occupies something of a sweet spot, not so close to Jupiter that its interior is dominated by violent volcanism, as Io's is, and not so far that tidal heating becomes too weak to sustain a genuinely liquid, potentially rock-contacting ocean, as may be the case for Ganymede and Callisto. This is not a coincidence born of nothing. It reflects the specific balance of distance and tidal stress that happens to fall in Europa's favor. It is one of the reasons Europa, rather than its larger, more ocean-rich neighbor Ganymede, has become the primary target for dedicated life detection missions. Jupiter's system is not, however, the only place in the solar system where this general pattern, ice shell, tidal heating, hidden ocean, has been found. In 2005, NASA's Cassini spacecraft, then in orbit around Saturn, made a discovery at one of that planet's smaller moons that would eventually provide something Europa has not yet delivered: direct sampling of a subsurface ocean's actual chemistry, gathered not through inference from a magnetic field, but by flying a spacecraft directly through material ejected from the ocean itself. The moon in question, Enceladus, is small, barely 500 kilometers across, a fraction of Europa's size. Cassini's cameras detected something unmistakable near its south pole. Towering plumes of water vapor and ice particles, erupting continuously from long fractures in the surface, nicknamed tiger stripes, rising hundreds of kilometers into space before falling back or, in some cases, escaping entirely to form one of Saturn's fainter rings. Unlike the disputed, intermittent plume signals reported at Europa, Enceladus's plumes are constant, well-documented, and thoroughly confirmed across more than a decade of repeated Cassini flybys. Crucially, Cassini did not merely photograph these plumes from a distance. It flew directly through them, using onboard instruments to analyze their composition directly. The results were striking. The plume material contained water, as expected, but also organic compounds, dissolved salts consistent with an ocean in contact with a rocky seafloor, and, in later, more detailed flybys, molecular hydrogen, a compound strongly associated on Earth with active hydrothermal vent systems of exactly the kind discussed in the previous chapter. Molecular hydrogen forming through water-rock reactions at Enceladus's seafloor would represent almost precisely the chemical energy source that chemosynthetic life relies on in Earth's steep oceans, detected not through indirect inference, but through direct chemical sampling of material that had, until recently, been in contact with the ocean floor itself. Enceladus does not prove that Europa harbors life, and the two moons differ in enough respects that conclusions cannot simply transfer from one to the other. But Enceladus does something almost as valuable for tonight's question. It demonstrates, with direct evidence rather than inference alone, that at least one icy moon in our solar system possesses precisely the combination of ingredients: liquid water in contact with rock, active hydrothermal chemistry, and organic compounds that scientists consider most promising for life. If nature has assembled this particular combination once, in one small moon of Saturn, the case for taking a similar possibility seriously at Europa, a larger, more massive world with its own strong evidence for an internal ocean, becomes considerably harder to dismiss as wishful thinking. The Sisters of Europa, it turns out, may be telling a story larger than any one of them individually, a story suggesting that ocean worlds, hidden beneath ice, far from any warming sun, may be a more common feature of our solar system than anyone suspected as recently as 30 years ago. It is worth pausing here to consider what this pattern might mean if it extends further still, beyond the handful of moons we have examined closely enough to test. Triton, Neptune's largest moon, shows geological signs, including its own history of resurfacing and a bizarre, youthful terrain unlike almost anything else in the outer solar system, that some researchers interpret as consistent with a subsurface ocean of its own, though evidence there remains far more limited than at Europa or Enceladus, largely because only a single spacecraft, Voyager 2, has ever passed close enough to gather data at all. Pluto, once dismissed as a simple ball of frozen rock at the solar system's edge, revealed through the New Horizons flyby in 2015, surface features that some scientists argue point toward a subsurface liquid layer beneath its own icy crust, kept from freezing entirely by a combination of radioactive heat and antifreeze compounds like ammonia, rather than the tidal heating driving Europa and Enceladus. None of these more distant candidates carry evidence as strong as what has been gathered at Europa and Enceladus, and it would be a mistake to treat speculative interpretation as though it carried the same weight as confirmed magnetic and chemical measurements. But taken as a group, the pattern is difficult to ignore entirely. Ocean worlds, once assumed to be a peculiarity unique to Earth, now appear to be turning up wherever spacecraft have looked closely enough to check, around Jupiter, around Saturn, and possibly extending even further out into the cold, poorly explored reaches beyond Neptune. If liquid water beneath ice turns out to be common throughout the outer solar system, rather than a rare exception, the question this documentary is built around stops being a question about one unusual moon and becomes a much larger question about how frequently the basic conditions for life may arise, quietly, in places far too cold and dark for anyone to have expected it. It is also worth acknowledging the moons we have not discussed in any detail, if only to keep tonight's account honest about the scale of what remains unexamined. Jupiter alone hosts 95 recognized moons beyond the 4 large Galilean bodies, most of them small, irregularly shaped objects likely captured by Jupiter's gravity long after the planet's initial formation, rather than born from the same circumplanetary disk as Io, Europa, Ganymede, and Callisto. Saturn's system holds well over 140 confirmed moons of its own, the vast majority far too small or too poorly observed to say anything meaningful about their internal structure at all. Somewhere among this enormous, largely unexamined population, other small pockets of liquid water may exist, entirely unknown to current science, simply because no spacecraft has ever passed close enough, carrying the right instruments, to check. The handful of ocean worlds discussed across this documentary are not necessarily the full inventory. They are, more accurately, the ones patient enough attention has so far managed to confirm. For Europa specifically, though, the strongest evidence remains where we left it at the end of the previous 2 chapters: an induced magnetic field, a chaotic, actively resurfaced ice shell, and a chemistry that plausibly supports the same kind of hydrothermal activity Enceladus has already confirmed through direct sampling. What Europa has not yet received is a mission built specifically to test these possibilities directly, the way Cassini tested Enceladus. That mission, however, is no longer a matter of speculation. It is already launched, and it is, at this very moment, somewhere on its long journey across the solar system, carrying instruments built for exactly this purpose. Building a spacecraft capable of investigating an ocean sealed beneath kilometers of ice, orbiting a planet surrounded by the most intense radiation belts in the solar system, is not a simple undertaking, and the mission that would eventually become Europa Clipper spent decades moving through proposal, revision, and delay before finally reaching the launch pad. Early concepts for a dedicated Europa mission date back to the 1990s, not long after Galileo's magnetic field data first suggested an ocean might exist. For years, funding and technical constraints kept these proposals grounded, as mission planners wrestled with a genuinely difficult engineering problem: how to operate sensitive instruments for years at a time, in close proximity to Europa, without those instruments being destroyed by Jupiter's radiation long before the mission could gather meaningful data. The solution that eventually emerged involved rethinking the mission's basic shape. Rather than placing a spacecraft directly into orbit around Europa, where it would sit continuously within the most intense portion of Jupiter's radiation belts, engineers designed Europa Clipper to orbit Jupiter itself, on a long, elliptical path that would carry it past Europa repeatedly, length after length, flyby after flyby, while spending most of each orbit farther from the planet, away from the worst of the radiation. This approach, using dozens of close flybys rather than a single continuous orbit, allows the spacecraft's instruments to gather data across nearly the entire moon over time, while limiting the cumulative radiation exposure that would otherwise degrade or destroy its electronics within a matter of months. Europa Clipper launched on the 14th of October 2024 from NASA's Kennedy Space Center, beginning a journey of roughly 1.8 billion miles that makes use of gravity assists from Mars and Earth to build up the speed needed to reach the outer solar system without requiring an impractically large amount of fuel. The spacecraft is scheduled to arrive at Jupiter and begin its work in April of 2030, at which point it will conduct 49 close flybys of Europa across the following years, at altitudes as low as 25 kilometers above the surface, close enough to gather detailed data, while still avoiding the most damaging radiation exposure a continuous low orbit would involve. Europa Clipper's instrument suite was designed specifically to test the open questions raised across this documentary so far, rather than to search for life directly, which remains beyond the reach of any currently planned mission. An ice-penetrating radar instrument will attempt to measure the thickness of Europa's ice shell directly and to determine whether the ocean beneath sits in contact with rock or is separated from it by an intervening layer of high-pressure ice. Precisely the unresolved question raised in Chapter 3 that so strongly affects the Moon's habitability prospects. A thermal imaging instrument will search for warm spots on the surface, potential locations where liquid water might be closer to the surface than elsewhere, or where plume activity, if it exists, might be more likely to occur. Mass spectrometers will analyze the extremely thin material surrounding Europa, including any material lofted from the surface, or should the disputed plumes prove real and the spacecraft happen to fly through one, material drawn directly from the ocean below. A second mission, launched by the European Space Agency, is making a similar journey through the same system with a complementary set of priorities. The Jupiter Icy Moons Explorer, known as JUICE, launched in April of 2023 and is scheduled to arrive in the Jupiter system in 2031, with a primary focus on Ganymede rather than Europa, though its trajectory includes flybys of both Europa and Callisto as well. JUICE will eventually enter orbit directly around Ganymede, the first time any spacecraft has orbited a moon other than Earth's own, allowing for sustained, long-term study of that moon's own subsurface ocean, complementing the flyby-based approach Europa Clipper is using at Europa itself. The two mission teams, based on opposite sides of the Atlantic and operating under different space agencies with different institutional cultures and funding structures, have nonetheless coordinated portions of their science planning, including efforts to schedule certain observations so that data gathered by one spacecraft can help interpret results returned by the other. A small but telling example of how a question this significant has drawn cooperation across what might otherwise have remained separate, competing national efforts. Together, these two missions represent the most ambitious and best instrumented investigation of the Jupiter system's ocean worlds ever attempted, arriving within roughly a year of each other after journeys measured not in months but in years. It is worth being precise about what these missions will and will not accomplish, because expectations set too high tend to curdle into disappointment when the actual results arrive. Neither Europa Clipper nor JUICE carries instruments capable of directly detecting living organisms. Neither will land on Europa's surface, drill through its ice, or sample its ocean directly. Engineering challenges of that scale remain for a future mission, likely decades away, that would only be justified once Clipper and JUICE have narrowed down where such an attempt would be most worthwhile. What these missions will do is close the largest remaining gaps in our understanding of Europa's habitability, the true thickness of its ice, the likelihood of rock-ocean contact, the presence or absence of active plume venting, and the detailed chemistry of its surface material. These are not small questions. They are, in fact, precisely the questions this documentary has repeatedly identified as unresolved across the preceding chapters, and by the early 2030s, for the first time in the history of this inquiry, direct spacecraft data, rather than inference, modeling, or extrapolation from Earth's own oceans, should begin to arrive. There is a particular kind of patience required to appreciate missions built on this timescale, and it is worth naming directly, because it says something meaningful about how science of this kind actually proceeds, generation after generation, long after any single researcher's own involvement has ended. The scientists who conceived early versions of a Europa mission in the 1990s will, in many cases, not be actively working when Clipper's full dataset is finally analyzed. Some of the mission's youngest team members were not yet born when Galileo first suggested an ocean might exist beneath Europa's ice. This is not a story that moves at the pace of a single human career, let alone a single evening's viewing. It moves at the pace of orbital mechanics, radiation shielding, and the slow, careful accumulation of engineering solutions to problems that took decades to even properly define. The record remains incomplete tonight, not because no one is looking, but because looking closely enough to answer a question this significant takes time, the same kind of patient, unhurried time that shaped Europa's ocean itself, one tidal flex at a time, across 4.5 billion years. Funding for missions on this scale is itself worth understanding, because it shapes why a project like Europa Clipper takes decades to move from proposal to launch. The mission's total cost, across development, launch, and operations through the end of its primary science phase, runs to roughly $5 billion, funded through NASA's planetary science budget and subject, at every stage, to competing priorities from missions studying Mars, the outer planets, and near-Earth objects considered relevant to planetary defense. Congressional appropriations, shifting agency priorities, and periodic reviews of cost and schedule all played a role in the mission's long path from early concept to an actual launch pad, and similar pressures will continue to shape whatever comes after Clipper, including any future mission built specifically to land on Europa's surface or sample its ocean more directly. Understanding this is not a distraction from the science. It is part of the honest picture of how discoveries at this scale actually happen, not purely through scientific curiosity, but through a slow, often difficult negotiation between what researchers want to know and what a society is willing to fund, sustained across administrations and budget cycles that can span an entire career. Even before Europa Clipper reaches the ice it was built to study, its long cruise phase has already produced smaller, unplanned contributions to Europa science, gathered almost as a byproduct of the journey itself. During its Mars Gravity Assist flyby in early 2025, the spacecraft's thermal imaging instrument was tested against the Martian surface to calibrate its sensitivity ahead of the Europa flybys still years away, a routine but necessary step in ensuring that when the spacecraft finally does reach its destination, its instruments will return data that scientists can trust without reservation. A second gravity assist, past Earth itself in December of 2026, will provide the final velocity boost needed to send the spacecraft the rest of the way toward Jupiter, arriving in April of 2030, roughly 5.5 years after its original launch. The engineering required to survive Jupiter's radiation environment long enough to complete this mission deserves a brief mention of its own, because it shaped nearly every design decision made during the spacecraft's construction. Europa Clipper's most sensitive electronics are housed inside a dedicated vault, its walls built from aluminium and zinc, thick enough to absorb a substantial portion of the radiation that would otherwise degrade the spacecraft's computer systems within weeks rather than years. Even with this shielding, mission planners calculated the total radiation dose the spacecraft would accumulate across its planned lifetime, and designed every instrument to continue functioning reliably up to, but not significantly beyond, that calculated limit, a careful balancing act between building a spacecraft robust enough to complete its mission and building one so heavily shielded that it would become too massive to launch using any available rocket. This same radiation environment is, incidentally, part of why a human mission to Europa's surface remains firmly in the territory of science fiction rather than realistic, near-future planning. Unshielded exposure to Jupiter's radiation belts at Europa's distance would deliver a lethal dose to an unprotected human being in a matter of hours, a hazard no current spacecraft technology can fully eliminate for a crewed vessel. This kind of layered, multi-year preparation reflects something true about the entire history traced across this documentary so far. Nothing about Europa's story has moved quickly. The moon itself took hundreds of millions of years to settle into the orbital resonance that drives its tidal heating. Galileo Galilei's original observation, in 1610, waited more than 3.5 centuries before a spacecraft bearing his name could test what that faint point of light was actually hiding. The Galileo mission's magnetic field data, gathered in the late 1990s, waited nearly 3 more decades before a dedicated follow-up mission was finally underway. And Europa Clipper itself, having launched in 2024, will spend most of the remaining years of this decade simply traveling, patient, unhurried, covering distance that light itself takes more than 40 minutes to cross before its real work can even begin. There is something worth sitting with in that pace, something that runs against the instinct of a species used to answers arriving quickly. The question of life beneath Jupiter's ice will not be answered tonight, or this year, or even by the time Europa Clipper completes its first handful of flybys. It will be answered slowly, through data gathered flyby by flyby, cross-checked against models built over decades, argued over in scientific papers written by researchers who understand, better than almost anyone, how easy it is to mistake an exciting signal for a real one. That patience is not a flaw in how this search is being conducted. It is the entire reason the search can be trusted at all. Before going further, it is worth pausing on a piece of this story that has nothing to do with Europa directly, but everything to do with why scientists studying it choose their words as carefully as they do. The search for life beyond Earth has a long history of premature excitement, and understanding that history helps explain the deliberate caution running through everything discussed so far in this documentary. In the summer of 1976, two NASA spacecraft named Viking 1 and Viking 2 landed on the surface of Mars, each carrying a set of biological experiments designed to test the Martian soil directly for signs of metabolic activity. One of these experiments, the labeled release experiment, produced a result that startled the scientists monitoring it in real time. When a nutrient solution was added to a soil sample, gas was released in a pattern that, on Earth, would strongly indicate biological metabolism at work. For a brief period, some members of the science team believed they might be looking at the first direct evidence of life beyond Earth. That excitement did not survive close scrutiny. Other instruments aboard the same landers, designed to detect organic compounds, the basic carbon-based molecules generally considered a prerequisite for life as we understand it, found essentially none in the same soil samples. This creates a genuine puzzle. How could soil show signs of biological activity while containing no detectable organic material at all? A combination that would be almost impossible to reconcile with any known form of terrestrial life, since every living organism on Earth is built from organic molecules and would be expected to leave some trace of them behind even after death. Over the following years, researchers proposed an alternative explanation, eventually finding strong support in later missions. The Martian soil contains highly reactive oxidizing chemicals, capable of producing gas releases through pure chemistry, with no biology required at all. The labeled release result, it turned out, was almost certainly a chemical false positive, not a biological signal. Nearly 50 years later, this remains a topic of ongoing, if now fairly narrow, scientific debate, with a small minority of researchers still arguing the biological explanation was dismissed too quickly. But the broad scientific consensus settled firmly on the non-biological interpretation, and it did so not through a single decisive test, but through years of accumulated evidence pointing consistently in one direction. A second episode arrived in 1996, when a team of NASA scientists announced findings from a meteorite named ALH 84001, recovered years earlier from Antarctic ice and identified as originating from Mars, ejected into space by an ancient impact before eventually falling to Earth. Inside the meteorite, researchers reported structures resembling microscopic fossils, along with chemical signatures they argued were consistent with biological activity that occurred on Mars billions of years ago. The announcement made headlines around the world, discussed publicly at the highest levels, including a formal statement from the sitting President of the United States. The scientific community's response, over the following years, was considerably more measured than the initial headlines suggested. Independent researchers re-examined the same evidence and found that every individual line of support could plausibly be explained through non-biological processes. The microscopic structures were smaller than any confirmed living organism on Earth and fell within a size range achievable through purely mineral processes, similar in form to structures that can form in certain terrestrial rocks, with no biological involvement whatsoever. The chemical signatures could form through inorganic reactions occurring during the meteorite's violent ejection from Mars, or its subsequent journey through space. No single piece of counter-evidence definitively disproved the biological interpretation, but taken together, the case for a non-biological origin grew steadily stronger, and the confident announcement of 1996 has, in the decades since, been walked back to something closer to an unresolved curiosity rather than a confirmed discovery. A more recent episode, closer to our own time, involves not Mars but Venus. In 2020, an international team of researchers reported detecting phosphine gas in Venus's upper atmosphere, a chemical compound that, on Earth, is strongly associated with biological processes and is difficult to produce through known non-biological chemistry in significant quantities. Venus's surface is far too hot and its atmosphere far too acidic for life, as commonly understood, but its upper cloud layers sit at a temperature and pressure roughly comparable to parts of Earth's own atmosphere, leading some researchers to speculate about the possibility of microbial life surviving in that narrow, temperate band. The announcement generated substantial public excitement, echoing headlines from both the Viking and ALH 84001 episodes decades earlier. Subsequent reanalysis, conducted by multiple independent research groups using different telescope data and different processing methods, produced conflicting results. Some teams found the original phosphine signal significantly weaker than first reported, or failed to replicate it at comparable confidence levels using their own datasets. Other researchers proposed non-biological chemical pathways that could plausibly generate phosphine within Venus's atmosphere through volcanic or photochemical processes not fully accounted for in the original analysis. As of the most recent published research, the phosphine question remains genuinely unresolved, neither confirmed nor conclusively ruled out, a state considerably more uncertain than the confident headlines of 2020 suggested at the time. These three episodes share a common structure worth naming directly. In each case, an initial finding generated significant excitement, sometimes amplified well beyond what the underlying data actually supported. In each case, that excitement was followed by years of careful, sometimes contentious re-examination, as independent researchers tested alternative explanations, hunted for chemical pathways that did not require biology, and gradually narrowed the range of interpretations the evidence could support. In none of these three cases has the scientific community reached confident, consensus agreement that life was actually detected. And in each case, the caution exercised after the fact stands in sharp contrast to the excitement expressed in the moment the finding was first announced. This history is precisely why the language used throughout this documentary has remained so consistently careful, chapter after chapter, from the first mention of an induced magnetic field to the most recent discussion of what a positive or negative result would actually mean. When Galileo's magnetic field data suggested an ocean beneath Europa's ice, the scientific community did not immediately announce that life had been found there. Because an ocean is not life, it is, at most, a necessary precondition for it. When Cassini detected molecular hydrogen in the plumes of Enceladus, researchers described it as consistent with hydrothermal activity, not as proof that anything living was actually present at the seafloor producing it. This restraint is not a lack of enthusiasm for the underlying science. It reflects hard-won institutional memory, built from decades of premature claims that did not survive scrutiny, and a professional culture that has learned, sometimes painfully, to distinguish between an intriguing signal and a confirmed discovery. It also explains why any account claiming NASA has already found life somewhere in the solar system, on Jupiter, on Mars, or anywhere else, and that this finding has been deliberately withheld from the public, deserves particular skepticism. Extraordinary claims of this kind tend to circulate widely online, often built around genuine scientific milestones, such as the launch of Europa Clipper itself, stretched or reframed into something the underlying facts do not actually support. The pattern across every genuine near miss in this history has been the opposite of concealment. Viking's ambiguous results were published openly and debated for decades in public scientific literature. The ALH 84001 announcement was made at a formal, televised press conference. The Venus phosphine findings were published in a peer-reviewed journal, openly available for any researcher anywhere in the world to challenge, and challenged they promptly were. Scientific institutions searching for life beyond Earth have, historically, erred toward announcing findings too early and too publicly, not toward hiding them. A genuine detection at Europa, whenever and if it eventually occurs, would very likely follow this same pattern. Published data, open scrutiny, and years of careful verification before anyone with real standing in the field would use the word confirmed. It is worth adding one further case to this record. Smaller in profile than Viking, ALH 84001, or the Venus phosphine debate, but instructive in its own way. In 2020, the same year as the phosphine announcement, researchers re-examining older data from Saturn's moon Titan proposed that certain unusual chemical patterns in its dense, hydrocarbon-rich atmosphere might be consistent with a hypothetical form of exotic biology adapted to Titan's extremely cold surface conditions, where liquid methane rather than water plays the role water plays on Earth. The proposal generated a brief wave of interest, followed swiftly by a broader scientific consensus that known, non-biological chemistry could account for the same observations without requiring anything as speculative as an entirely alternative biochemistry. Titan remains a genuinely compelling world for reasons that have nothing to do with this particular claim, but the pattern here matches the others closely. An intriguing signal, a burst of public attention, and a more measured scientific response that ultimately found ordinary chemistry sufficient to explain what had briefly seemed extraordinary. None of this history should be read as pessimism about Europa's prospects specifically. If anything, the opposite is true. The very fact that scientists have learned to move this carefully is part of why the accumulated evidence for a European ocean, built across decades, tested from multiple independent directions, and never definitively contradicted by an alternative explanation, carries as much weight as it currently does. The record has not offered false hope so much as it has offered a series of hard lessons in patience, and those lessons are precisely what shape how the coming decade of Europa exploration will be conducted and reported. Once real data finally begins arriving from a spacecraft built specifically to gather it, it is worth spending some time on a question this documentary has, until now, largely set aside. What would it actually mean, practically and scientifically, if a future mission eventually did find evidence of life in Europa's ocean? The answer is less dramatic and considerably more interesting than the phrase "finding life" tends to suggest in popular imagination. No mission currently planned, including Europa Clipper and JUICE, carries instruments capable of directly imaging a living organism or unambiguously identifying one as biological in origin. What these missions, and any realistic near-future follow-up, could plausibly detect is evidence consistent with life, organic molecules of a particular complexity, chemical imbalances in the ocean that are difficult to explain through geology alone, or, in the most optimistic scenario, biosignature gases sampled directly from a confirmed plume, similar to the molecular hydrogen Cassini found at Enceladus, but potentially including compounds even more strongly associated with active metabolism. Any of these findings would represent a genuine, significant advance. None of them would constitute the kind of unambiguous, headline-ready confirmation that popular culture has trained audiences to expect from a story about alien life. This matters because the actual scientific process, if it eventually does find something significant at Europa, will very likely resemble the earlier chapters of this documentary far more than it resembles a single dramatic announcement. A promising signal detected by Europa Clipper would prompt cautious, qualified publication in scientific journals, consistent with, rather than proof of. That publication would trigger years of scrutiny from independent researchers, searching for the same kind of non-biological explanations that ultimately accounted for the Viking, ALH 84001, and Venus phosphine results. If those alternative explanations failed to account for the data as convincingly as a biological explanation did, and if the signal held up across repeated, independent measurement, confidence would gradually build, not through a single moment of certainty, but through the same slow accumulation of evidence that established Europa's ocean itself as scientific consensus in the first place. This is, admittedly, a less satisfying story than the one popular headlines tend to promise. There will likely be no single press conference at which humanity learns, definitively and all at once, that we are not alone. What is more likely, if the underlying reality supports it, is a gradual shift in scientific confidence, tracked across years of publications, conferences, and follow-up missions, until a point is reached where the scientific community broadly agrees that no plausible non-biological explanation remains. That point, if it is ever reached for Europa, may not arrive within the lifetime of anyone watching this documentary tonight. It may arrive within a generation. It may take considerably longer. The Keeper cannot offer a date, because no honest account of this science currently can. What can be said, with more confidence, is what such a finding would mean for how we understand life itself, regardless of the exact timeline on which it arrives. Every confirmed example of life humanity currently possesses traces back to a single origin on Earth, some 3 to 4 billion years ago. Every organism ever studied, from the simplest bacterium to the largest whale, shares the same fundamental genetic code, the same basic biochemistry, descended from that single starting point. This means that everything we currently know about life is drawn from a sample size of exactly 1. We do not know, with any confidence, whether the specific chemistry that gave rise to life on Earth was close to inevitable given the right conditions, or whether it was an extraordinarily improbable event that might not repeat itself even given billions of similar opportunities across the universe. A confirmed second origin of life, even a simple one, even a single organism, provided it could be shown to have arisen independently from Earth's own biology, rather than having been transported there by some contamination pathway, would answer this question decisively, in a way no amount of theoretical modeling ever could. If life arose independently at Europa, entirely separate from Earth, using perhaps a different genetic chemistry, a different set of basic molecular building blocks, then the sample size for how often life arises, given the right ingredients, would double immediately from 1 to 2. And a sample of 2, found within a single solar system, in 2 entirely different environments, sunlit surface and dark subsurface ocean, would reshape how confidently scientists could estimate the odds of life arising more broadly across the universe, wherever similar conditions exist. This is the real weight carried by tonight's question, and it has little to do with the sensational framing that so often surrounds discussions of alien life. It is not primarily a question about monsters in the deep, or first contact, or civilizations we might someday meet. Europa's ocean, even in the most optimistic scenario currently supported by evidence, is far more likely to hold something closer to bacteria than anything resembling intelligence. Simple, single-celled organisms, if anything at all, adapted to a lightless, high-pressure, chemically driven existence utterly unlike life on Earth's surface. That may sound modest. It is not. A second, independent origin of even the simplest life would be among the most significant discoveries in the history of science, reshaping our understanding of biology, chemistry, and our own likely place within a universe that may turn out to be far more thoroughly, quietly alive than anyone currently has reason to claim with confidence. It is worth briefly considering what kind of life, if any, is eventually found. Current models suggest is most plausible, if only to keep expectations grounded in something more specific than the word life alone can convey. Researchers who study this question generally point toward the simplest possible candidates: single-celled organisms broadly comparable to Earth's own extremophile bacteria, the kind that already thrive in Earth's harshest known environments, including hydrothermal vents, the interiors of Antarctic ice, and rock formations kilometers below the surface, entirely without sunlight. These Earth-based extremophiles serve as a useful reference point precisely because they demonstrate that life, at least on our own planet, is considerably more adaptable to darkness, pressure, and chemical extremity than the sunlit world most people picture when they imagine a living ecosystem. If Europa's ocean holds anything at all, current thinking suggests it is far more likely to resemble these hardy, unglamorous microorganisms than anything resembling a more complex or recognizable creature. There is also a narrower, more immediate implication worth naming, separate from the grand question of life's frequency across the universe, and closer in scale to the kind of result a mission like Europa Clipper is actually likely to return within its own operational lifetime. Even a confirmed negative result, a thorough, well-instrumented investigation of Europa's ocean that finds no evidence of biology at all, would carry real scientific value, though it rarely receives the same attention in public discussion that a positive finding would. A confirmed absence of life in an environment that otherwise appears to hold every necessary ingredient, liquid water, chemical energy, and billions of years of stable conditions, would suggest that something else, some additional factor not yet identified, is required for life to actually begin. Identifying what that missing factor might be would itself represent significant scientific progress, narrowing the search for life elsewhere by ruling out one of the most promising candidates currently under consideration and forcing a re-examination of exactly what conditions life actually requires beyond the 3 ingredients discussed earlier in this documentary. Consider, in this light, an analogy drawn from a very different field of science, one that may make the stakes of a negative result easier to appreciate. For much of the 20th century, physicists searched for a theoretical particle known as the Higgs boson, a discovery finally confirmed in 2012 after decades of theoretical prediction and billions of dollars invested in building instruments capable of detecting it. Had the particle not been found, despite such enormous investment, the result would not have been dismissed as a wasted effort. It would have forced a fundamental rethinking of the entire theoretical framework that predicted the particle's existence in the first place, arguably a more significant scientific event than confirmation would have been, precisely because it would have revealed that our best existing understanding was somehow incomplete in a way nobody had previously identified. A thorough, well-instrumented search for life at Europa that comes back empty would occupy a similar scientific position, not a failure, but a genuine constraint on our understanding of what life actually requires, forcing precisely the kind of theoretical reconsideration that drives science forward regardless of which direction the answer ultimately points. This is worth remembering because it reframes what success actually means for a mission like Europa Clipper. A mission is not a failure simply because it does not return evidence of biology. Confirming the precise thickness of Europa's ice, resolving whether the ocean contacts rock directly, and measuring the chemistry of the surface material in detail would represent enormous scientific progress, regardless of what those measurements ultimately reveal about the presence or absence of life. Every honest account of this search must hold both outcomes as genuinely possible, without allowing enthusiasm for one to distort how the eventual result, whatever it turns out to be, gets reported and understood. There is a temptation, in discussing questions this large, to reach for language beyond what the evidence supports, to speak with more certainty than the data allows. In either direction, simply because the stakes of the question feel too significant to sit comfortably with an honest, "we do not yet know." That temptation deserves to be named and resisted directly, and it applies as much to unwarranted excitement as it does to unwarranted dismissal. A viewer coming to this subject for the first time might reasonably expect either a confident yes or a dismissive no, when the truthful answer, at least for now, is neither. Whatever Europa's ocean eventually reveals, whether it holds a second, independent origin of life or holds nothing living at all, the value of the search does not depend on which answer arrives. The value lies in asking the question as carefully and as honestly as the evidence allows, the same careful, unhurried approach that has carried this story from a single point of light in Galileo's telescope, through decades of magnetic field data and mission proposals, to a spacecraft now crossing the solar system to finally look closely enough to find out, step back far enough from the specific mechanics of magnetometers and mass spectrometers, and tonight's question reveals itself to be an old one, dressed in modern instrumentation. Human beings have wondered whether they were alone in the universe for as long as there has been a written record of human thought, long before anyone understood what a planet was, let alone what a moon of Jupiter might be hiding beneath its ice. What has changed, across the span of only a few centuries, is not the question itself, but the tools available for approaching it, from pure speculation to careful observation through Galileo's small telescope, to spacecraft now capable of crossing 1 billion miles of empty space to gather a direct answer. It is worth remembering, in this light, how recently Europa's ocean itself became something science could discuss with genuine confidence rather than pure conjecture. For nearly all of human history, this small moon was, at most, a faint point of light, indistinguishable in any meaningful sense from a star. For most of the 20th century, once telescopes and later spacecraft revealed it as a world in its own right, it was assumed to be frozen through, uninteresting, a minor footnote in the story of the outer solar system. The ocean beneath its ice, quite possibly the largest single body of liquid water known to exist anywhere beyond Earth, has been part of confident scientific understanding for barely 30 years. In the 4.5 billion year history traced across this documentary, 30 years is not even a rounding error. And yet, within that brief span, our understanding of what this small, distant world might be hiding has been transformed almost entirely. This is, in its way, the deepest lesson tonight's question has to offer, independent of whatever Europa Clipper eventually finds when it arrives in 2030. The universe does not reveal its contents all at once, in a single dramatic disclosure. It reveals them slowly, patiently, often reluctantly, to whoever is willing to keep asking, keep measuring, keep testing one explanation against another until only the strongest survives. Jupiter's storms have been raging for at least 3 centuries that we know of, and almost certainly far longer than that. Europa's ice has been cracking and refreezing for billions of years, moved by a tidal heartbeat no human being witnessed until the closing decades of the 20th century. The ocean beneath that ice, if it holds anything at all, has been holding it quietly, undisturbed, since long before there was a species on the 3rd planet capable of wondering about it. There is something worth carrying from that scale of patience into ordinary life, beyond the specific science of icy moons and subsurface oceans. Not every question yields to force, or speed, or the desire for an answer to arrive on a convenient timeline. Some questions, the best ones, perhaps, the ones that matter most, only yield to sustained, careful, unglamorous attention, extended across years or decades, by people willing to keep looking long after the initial excitement of the question has settled into the slower, steadier work of actually finding out. Europa's ocean has waited 4.5 billion years to be asked a direct question by something built specifically to ask it. It can wait a little longer, through the remaining years of Europa Clipper's cruise, through the flybys still to come, through the careful, incremental process of turning data into confidence. What if there is life beneath Jupiter's ice? Tonight, that question remains open, exactly as honest science requires it to remain, resting on a foundation built from magnetic field measurements, chemical inference, and the hard-won caution of a field that has learned, through repeated experience, not to mistake hope for evidence. The ocean is there, or very likely there, held liquid by a gravitational relationship as old as the moon itself. Whether anything living has ever stirred within it is a question the ice has kept to itself for the whole of Earth's own history. Through every extinction, every ocean that has risen and receded on our own planet's surface, every species that has come and gone while that dark water sat, undisturbed, beneath its frozen shell, it may keep that answer a little longer still. But for the first time since anyone first wondered, a spacecraft is finally on its way to ask. There is a particular image worth holding on to as this documentary begins to draw toward its close. Somewhere beneath a shell of ice thick enough to bury the tallest structures ever built on Earth many times over, in water that has never once seen sunlight, minerals dissolved from rock meet chemicals delivered from a surface being constantly reworked by radiation, in a chamber warmed not by any star, but by the patient, mechanical squeezing of a planet's gravity. Whatever is or is not happening in that water, the water itself is real, supported by the strongest evidence current planetary science can offer without physical contact. It has been there, doing whatever it does, for longer than there have been eyes anywhere in this solar system capable of appreciating it, longer than the dinosaurs walked Earth's surface, longer than complex animal life has existed on our own planet at all. Consider, too, what it says about the character of scientific discovery that this entire story, from Galileo's first glimpse of an unexplained point of light, to a spacecraft now crossing the solar system with purpose-built instruments, required no single genius insight, no sudden breakthrough that changed everything at once. It required generations of researchers willing to add one small, careful piece of evidence to the next, a photograph here, a magnetic reading there, a comparison to deep-sea vents discovered almost by accident on the other side of the solar system entirely, a plume of vapor caught by chance in an image of a much smaller, much colder moon of Saturn. No one person could have arrived at tonight's picture of Europa alone. It took centuries, and it will likely take a few decades more before the picture is anywhere near complete. That, too, is worth sitting with quietly as this night draws on, the reminder that some of the most significant questions available to us are not answered by anyone in particular, but by an accumulation, across generations, of people willing to keep looking a little longer than the last person did. It is fitting, in a story built so heavily around scale and patience, to end this chapter by returning briefly to the beginning of the solar system itself. The same disk of gas and dust that formed the Sun, that formed Jupiter, that formed the ice now sitting quietly above Europa's ocean, also formed Earth and everything living on it, including whoever is listening to these words tonight. Every atom of hydrogen in Europa's hypothesized ocean and every atom of hydrogen in a human body trace back, ultimately, to the same origin, either forged in the first moments after the Big Bang or assembled later inside the nuclear furnaces of stars that lived and died long before our own sun ever ignited. In this sense, whatever the ice above Europa's ocean is or is not hiding, it is not hiding something entirely foreign to us. It is built from the same raw material, shaped by the same physical laws, sitting quietly in a slightly colder, slightly darker corner of the same solar system we call home. Consider, finally, the strange symmetry in how this story began and how it currently stands. It began with a single observer, alone at night, pointing an imperfect instrument toward a bright planet and noticing 4 small lights that did not belong where they were supposed to be. It stands today with an international effort spanning multiple space agencies, thousands of engineers and scientists, and spacecraft built from materials and technologies Galileo could never have imagined, all directed at the same basic question his simple observation first made possible to ask. What else might be out there, quietly orbiting, waiting to be noticed by whoever happens to be paying close enough attention? The scale of the effort has changed enormously. The underlying curiosity driving it has not changed at all. And so the record, for now, rests exactly where the evidence leaves it, neither confirming life beneath Europa's ice nor ruling it out, but establishing, through decades of patient, independently verified work, that the question deserves to be asked as seriously as any question currently before science. That is not a small conclusion, even if it lacks the drama of a headline. It is the conclusion the evidence actually supports, offered honestly, without embellishment, in the same spirit that has carried this story from a handmade telescope in 1610 to a spacecraft now somewhere between Earth and Jupiter, carrying instruments capable, for the first time, of asking the ice directly, close. There is no tidy way to end a story that is still being written, and this one is very much still being written. Europa Clipper is, at this moment, somewhere along its long, patient arc through the solar system, still years from the flybys that will finally test the questions this documentary has spent so long laying out. JUICE follows a similar path, on its own timeline, toward a different but related target. Neither spacecraft carries an answer yet. They carry only the instruments capable of eventually finding one, and the years of careful engineering that made reaching this point possible at all. What can be said, honestly, is this. Beneath a shell of ice that has kept its secrets since before there was any species anywhere capable of asking about them, water almost certainly exists in liquid form, vast, dark, and warmed by a mechanism as old as the moon itself. That water sits in contact, directly or indirectly, with rock that may be delivering the same basic chemistry that gave rise to life in Earth's own deep oceans billions of years ago, in conditions not entirely unlike the ones Europa's ocean may hold today. Whether anything living has ever taken hold in that darkness remains genuinely unknown, and will very likely remain unknown for some years yet, resolved only through the slow, unglamorous work already underway. There is one further point worth carrying forward, drawn from something discussed earlier in this documentary, but easy to lose sight of by the time an ending arrives. This search has never depended on a single dramatic proof, and it will not conclude with one either. It has been built, chapter by chapter, from magnetic field readings that took years to interpret, from surface images that took decades to explain, from a chance discovery in Earth's own deep ocean that changed how an entire field thought about the requirements for life, and from the accumulated caution of scientists who have learned, through repeated experience, exactly how easy it is to mistake enthusiasm for evidence. None of these pieces, alone, would have been enough. Together, they have built something considerably more durable than a single headline ever could. A genuinely well-supported case, open to revision, resting on evidence rather than hope, for taking seriously the possibility that Europa's ocean holds something more than water and rock. This uncertainty is not a disappointment. It is the honest shape of the question as it currently stands, and there is something worth valuing in an answer that has not yet been rushed. The scientists who built Europa Clipper, and the ones who will spend the coming decade analyzing what it returns, are not chasing a headline. They are doing something slower and, in its way, more durable, adding one more careful piece to a picture that has been under construction since a single observer in 1610 first noticed 4 small lights where none were supposed to be. Somewhere out past the asteroid belt, past the reach of any light bright enough to warm it, a moon smaller than our own continues turning through the dark, squeezed gently by the same gravity that has shaped it since before Earth's own oceans first filled with anything alive. Its ice keeps moving, slowly, the way it always has, folding and refreezing along ridges first noticed in blurry photographs sent back by 2 aging spacecraft nearly half a century ago. Its ocean, If the evidence gathered so far is trusted, keeps its own quiet chemistry running, undisturbed, the way it may have been running for 4.5 billion years, warmed by a gravitational pull that has never once paused to rest. Whatever that chemistry has or has not become in all that time, it has been patient. It can, for a little while longer, remain exactly what it is, a question, carefully asked, still waiting on its answer.